All right, let's talk about something we do dozens, maybe hundreds of times a day without even thinking about it. Every time you click a link, send a message, or watch a show, you're kicking off this incredible hidden journey. We're going to pull back the curtain on how the internet actually works.
So you click something and boom, it's there. It feels like magic, right? Like it's instantaneous. But it's not magic at all. It's actually a super high-speed race across the planet. And the star of the show is this tiny, unsung hero, the data packet.
So, meet our hero, the packet. You can think of it like a tiny digital envelope. It's just a small piece of the website or data you're asking for, and its mission, should it choose to accept it, is to get from your computer to a server, maybe thousands of miles away, and bring a response back.
Okay, so the moment you make that request, our packet's journey officially begins. But it can't just wander out onto the internet by itself. First, it needs to get properly addressed and stamped for the trip.
Inside this digital envelope are its travel documents. You've got the source and destination IP addresses. That's basically the from and to address. You've got the protocol, which is the language it's going to speak when it gets there. And then you have this thing called the time to live, or TTL. Think of it like a countdown timer, and we're going to see why that is so important in a little bit.
All right, our packet's all addressed and ready to roll. What's its first challenge? Well, it's just getting out of its own neighborhood. Your home or office network.
Your computer takes a quick look at its local map and sees, hey, this destination address isn't around here. So it does the only thing it can. It sends the packet to the designated exit door. We call this the default gateway. And for most of us, it's our Wi-Fi router. It's the single point of contact for any and all traffic that needs to leave the local network. Okay, so now our packet is at the router. This little box has to make a really critical decision. In just a fraction of a second, it has to look at our packet and figure out the absolute best path to send it on, out of, well, millions of possibilities.
So how does it do it? Well, it's not guessing. It immediately consults its internal rulebook, which we call a routing table. You can literally think of this as the router's built-in GPS. It's a map that lists all the networks it knows about and the best way to get to them.
Now, this might look a little technical, but it's pretty simple. The router is just trying to find a match for our packet's destination. But what's really interesting is that last entry, the one with all the zeros. That's the default route. It's the router's way of saying, if I don't have a specific road for this, I'm just going to send it this way to the next router and let them figure it out. But what if there are multiple possible matches?
The router follows a very strict three-step logic. First, it always picks the most specific route. A route to a single street is always better than a route to the whole city. If there's a tie, it looks at administrative distance, which is just a fancy way of saying which source of information do I trust more. And if they're still tied, it finally looks at the metric, the cost of the path, and picks the one that's fastest or shortest. Decision made, and our packet is sent on its way.
So our packet has a clear path forward now. It's on its way, but here's the thing. Just because you have a map doesn't mean you have a free pass to go wherever you want. It's got to get through security first.
And this is a really important distinction to make. These are two totally different jobs. The route table is the GPS. It answers the question, which way do I go? But a security group or a firewall, that's the bouncer at the door. It doesn't care about directions. It only asks one question. Are you on the list? Are you allowed in?
This quote from a contributor on Stack Overflow just nails it perfectly. You have to have a path first. I mean, if the GPS says there are no roads to get to your destination, it doesn't really matter if you have a VIP pass, right? You're just not getting there. Routing always comes before filtering.
So this process repeats itself. The packet jumps from router to router, hop by hop, across the world. But what happens when the road ahead is broken? Or worse, what if a confused router sends our packet in circles?
Remember that time to live value we talked about? This is where it becomes an absolute lifesaver. It's not actually about time at all. It's a hop counter. Every single time a router forwards the packet, it subtracts 1 from that TTL number. If that number ever hits 0, the packet is just discarded. It's a fantastic, simple safety net that prevents a lost packet from bouncing around the internet forever and causing a massive traffic jam.
This is exactly what's happening under the hood when you run a tool like Traceroute to figure out why a connection is failing. It sends out packets and uses the TTL to map the journey, hop by hop. And when you see those asterisks, that means a router on the path didn't respond. That's your smoking gun. That's probably where the problem is.
And the causes for these issues can be anything, really. Sometimes it's a simple hardware failure, or maybe a typo in a router's configuration.
Other times it's just plain old network congestion, or even something more sinister, like a malicious attack. This is why having these robust systems in place is so critical.
Okay, our packet has made it a long way. But think about this. This exact process is happening for trillions of packets every single second. So, how does the entire internet not just collapse under its own weight?
I mean, seriously, if every router in the world had to know the specific path to every single other device on the planet, their internal GPS, that routing table, would be impossibly huge. No computer could handle it. So, what's the solution? Well, it's a really elegant concept called Route Summarization.
So, without summarization, a router's table would look something like this. It would have to list every single tiny network, every street, if you will. Millions and millions of entries. It's just completely unmanageable and incredibly inefficient. But with summarization, instead of listing every single street, a router can just advertise the entire region. This one single line here replaces all of those previous ones. It's basically the router shouting, hey, if you need to get to this general area, just send the packet to me. I know the local roads, and I'll take it from here.
And this is why it is so profoundly important. It gives us smaller, faster routing tables. It means way less chatter between routers when things change. And it creates stability, because the problem in one small corner of the internet doesn't cause a global traffic jam. This technique is, without a doubt, one of the core reasons the internet can even exist at a global scale.
So from a simple click on your screen to a complex, globe-spanning journey, the adventure of a single packet is this hidden marvel of engineering. It's governed by logic, protected by security, and made efficient by clever ideas. A system that connects us all one hop at a time. But as our networks get smarter, with AI and automation on the horizon, you have to wonder, what's next?